Today's lesson is day 2 of Chapter 3 curve fitting. Just make sure this is zoomed in and focused. Alright, starting from the top of today's handout, it says, prior to this lesson, we learned how to use our graphing calculators to calculate an exponential equation of best fit. We will be extending that skill to include other models of best fit and how to mathematically decide which model is best for a given set of data. So for the example we're going to use to start today's lesson, input the following data into your calculator. Anytime you do anything data-driven on the calculator, you want to go to y equals, make sure you clear out the equations. Make sure your stat plots are turned off. I'm going to zoom 6 to get rid of any weird window dimensions that may be left over in there. And then stat edit, and we'll clear out any old data that's in there. Alright, so putting in the new data, we have 5, 10, 15, 20, 25, 30 for the x values. The y values, we have 6, 25, 40, 95, 172, 275. Double check to make sure they're in correctly. If you start off with the data being incorrect, pretty good chance of most of everything else you do will be wrong as well. Alright. Next, we're going to create a scatter plot. Second stat plot, they should all be turned off right now. Turn it on, turn number 1 on. Scatter plot option, the data is an L1, L2. How you mark it and what color you use doesn't matter. I am going to build a window that makes sense in the context of this problem. My x's go from 5 to 30, so I'm going to go like -5 to 40. So I can see the axes with a negative number, and 40 is a little bit beyond the largest number. Scale up by, say, 5. The y's are going from 6 to 275, so make the y max like 300. Make the y min, that -10 will probably work out well. Scale up by, say, I don't know, 25. The stuff at the bottom we don't have to worry about. I will hit graph and see what we get. So it looks like we have the beginnings of what appears to be an exponential growth type of graph. Calculate the exponential regression equation of best fit. So I am going to go to stat calc. expreg is one of the ones we used yesterday. L1, L2, frequency list blank. We want to store that regression equation right in Y1. Alpha F4, Y1. Calculate. And does it give rounding instructions on here anywhere? Nope, leave it on rounding. Okay, I'm going to take a peek. It put the equation into Y1. I'm going to hit graph. So it looks reasonably good. It's rare to have a curve of best fit where it hits every data point exact, but that certainly seems reasonable. So let's see what they want us to do next. So create a scatter plot, we did it. Calculate the exponential regression equation of best fit, we did it. Graph your equation in the same window with the scatter plot, did it. How well does the curve fit the data? That we just kind of talked about. Now, can we do better? Is there another equation or another model of an equation that will be a better fit for this data than what we found? So one thing that we're going to consider, if it can be fit with an exponential, very often a power regression can give a similar type of fit. So that's what I'm going to do next. I'm going to go back to stat, calc, and I'm going to choose the PWR regression equation. The data is in L1, L2. It's the same data. Frequency list, we still want blank. We'll put this equation into, did it again with that mistake, into alpha, start over. I messed that up pretty good, I apologize. Stat calc, power reg, alpha F4, put it in Y2, calculate, and then take a peek. So they both appear to hit that point. The red fits it a little bit better than the blue. The blue fits it, but the red misses. Red fits, blue misses. Blue is a little bit closer with that. Blue maybe is a little closer than that one with the red. So visually speaking, it's tough to really argue, well, which one of these fits better? Is it the power or is it the exponential? We're going to look at a mathematical way to decide which is better. Before we get to that, let's take a look at the actual models themselves. So I'm going to rerun the exponential of best fit. Stat, calc, exp reg. And I'm not going to store it. I already have it stored. Just going to calculate it. So if you do an exponential reg, it's going to give you the equation, and y is equal to a times b to the x form. And then for this one, a, if we just go 2 decimal places, is about 4.16. B is about 1.16. Okay, the power reg, I'll rerun that again. Stat calc, power reg, calculate. Here, it's y is equal to a times x to the b power. And a turned out to be about 0.19 if we just do 2 decimal places for quick comparison, 2.10, round that to 2 decimal places. So with an exponential reg, it's a constant raised to a variable exponent. In power reg, it flips that orientation. It's the variable to a constant exponent. Now for some data, you can get very similar curves, and for some data, they'll be significantly different. So for today's activity, the question is, which of those two is the better option? In terms of just visual impression, it's really tough to argue one way or the other in terms of which one is better. So here's what we're going to do. Two terms, correlation coefficient and coefficient of determination. The correlation coefficient, which is pretty universally labeled with the variable r, is the measure of the strength of the linear association between two variables. The maximum value for r is a positive 1, and r close to 1 indicates a strong positive association. Okay? The positive refers to the data rising to the right. The minimum value for r is negative 1, and r close to negative 1 indicates a strong negative association. So if your data is falling to the right, that's a negative association. Now it says linear association. This is a curve. The calculator actually does a lot of stuff in the background in order to calculate that r. It does what's called linearizing the data and then does a set of calculations. Those of you that have already completed AP Stat, we spent quite a bit of time talking about what the calculator actually does to produce that R value. Those of you that are currently in AP Stat, we're going to be getting to that in chapters 3 and chapter 12 towards the end of the course. Okay, for the most part, we don't really care for this particular course about the names for the R and the R squared, which we're going to get to in a minute. The important thing that we're concerned with right here, right now, is that if your R value is close to positive 1 or negative 1, then for what we do in this class, that's an indicator that that equation fits the data very well. Okay, Now, from R, you get R squared. That's known as your coefficient of determination. That's the percent of variation in Y that can be explained by the least squares regression line of Y on X. Okay, that's the definition as it appears in the AP Stat textbook. Again, we don't really care about this definition very much. This is the important stuff that follows. If R is equal to 0.8, then R squared is equal to 0.64. If you square 0.8, that's the number you get. Okay, typically you think about R squared as a percent. So a very watered down interpretation of this right here is 64% of the observed variation in Y can be explained by knowing X. That means 36% is due to some other factor or factors. Okay, again, focusing on what we want to know for this particular class. The correlation coefficient and or the coefficient of determination can be used as an indicator to how well an equation fits a set of data. When using R as the parameter in comparing which curve fits the data, the curve that has an R value closer to positive 1 or negative 1 is the better fit. When using R squared as the parameter in comparing which curve fits the data, the curve that has an R squared value closer to 1 is the better fit. All right, now those of you that have already completed AP Stat, we spent quite a bit of time talking about this. There are considerations other than correlation coefficient and coefficient of determination when deciding what model fits a data set. However, these are beyond the scope of our curriculum and will not be addressed in this class. Again, that's venturing into AP statistics territory. All right, we will obtain R and R squared by using graphing calculators. The process of how those values are obtained are not within the scope of this course. Okay, that's part of, again, AP statistics. You learn all the inner workings of where those numbers come from. I'm going to show you what calculator keystrokes we need to use to get them on the calculator, and then we'll go from there. Okay, key thing is diagnostics must be turned on in any of the 83, 84 family of calculators in order to get those values when you're finding a curve fit. So this is how we're going to turn them on. Okay, if you go to second 0, that accesses the catalog in the calculator. This is the various different commands that are available to you or programs that are available to you. We want to get the diagnostics on. We can scroll all the way through the A, B, C's, etc. of all the different options we have, or you can just hit the X to the -1 button, which corresponds to an alpha D. We want diagnostics on, and we have to hit that twice. So what happens now when your diagnostics are turned on, when you do certain curves of best fit, you're going to get the R and the R squared value. So I will rerun again. Exponential reg. And R, go 3 decimal places, 0.983. R squared, 0.966. Excuse me. I am going to rerun the EXP reg, the power reg. R is 0.993 to 3 decimal places. R squared is 0.985. So turn your diagnostics on in your graphing calculator and recalculate the exponential and power equations of best fit. So now that we've redone this, oops, I wrote that down. It was not appearing on this window. I apologize. Those are the values. So you can compare R to R or R squared to R squared. For what we do in this class, it doesn't matter which one you choose. What you can't do is compare an R to an R squared or an R squared to an R. So based on our values, the 0.993 is closer to 1 than the 0.983. The 0.985 is closer to 1 than the 0.966. So no matter which of the comparisons that you decide to use, the power, based on what we do in this class, is the better mathematical choice. Emphasizing again, in statistics classes, not just AP Stat, but any upper level statistics class you take, meaning like higher high school or lower level college, there are other considerations other than just R and R squared. But for what we do in here, those are the ones we're focusing on. So based on your R squared values, which model fits the data the best, the power is better. Okay, using the model you choose, predict Y when X is 18, when X is 50. So what I'm going to do is I am going to go to my Y equals screen. I'm using the power model here to answer these questions. I may need to go back and use the exponential for other things, so I'm just going to de-highlight that equal sign rather than delete it out. All right, when you're making predictions on your calculator and it's in a direction of an X, given an X, find a Y, one thing you could do is use a trace feature. Okay, once you hit trace, it tells you what you're tracing. We want to trace the curve. So I'm going to hit the down arrow button to get on the curve, and then type in the X value that I'm interested in, 18. So when X is 18, Y is about 80.6. Does it have round off instructions anywhere? No, we'll just go 80.6. Okay, then I'm going to hit trace, trace, I forgot to go onto the curve, 50, and I get an error message. Okay, if you try to trace to a value that's outside your window, my X max is only going to 40. So I need to get an X value of at least 50, so we'll make it 60 in order to be able to trace to it. So if I hit trace, finish graphing, go down onto the curve, type in 50, gives me an X value, a Y value of about 688.7. Okay, the other thing that I could very easily do, I could go to my table set, put it to Ask Auto, go to my table, type in 18, type in the 50, and get the two values that way. All right, last thing they're asking us to do here. Predict an X given a Y. Okay, for this one here, the trace feature is not going to work. So what we need to do for this, if we're going to solve it by using the graphing capabilities of our calculator, is we are going to put in the 130 and the 500 as their own individual equations. So I can definitely see the point of intersection for where the line 130 crosses it, but I'm not seeing a line for 500. That's because my Y max is only going up to 300. So we'll increase that to say 550. Graph. And now I can see both intersection points. So this one down here, when Y is 130, X is about 22.6. Make sure you follow whatever the rounding instructions are. That one. And then when Y is 500, jump to the next curve, enter, about 42.9. Okay, something I mentioned in yesterday's lesson, for those of you that had AP Stat last year, in AP Stat we only did predictions in a direction of given an X, find a Y. We didn't do predictions in reverse. In AP Statistics, that's considered frowned upon. These predictions aren't considered very valid. They're good enough for what we do in this class in order to make that reverse prediction. We go both ways with that. All right, that's a wrap in terms of the actual lesson here. What I want to do is talk a little bit about the homework to make sure that everyone's okay on expectations in terms of what needs to be done. All right, so this is tonight's homework. We're given a data set here. We're going to get that into your calculator. You're going to calculate an exponential of best fit. You're going to state it. State the R and the R squared. Make some predictions. And then they're going to ask you a residual question. If you don't recall how to do that, refer back to yesterday's notes. Okay, similar thing. Power. They're going to give you a data set. Calculate a power of best fit. What are your R and R squared values? Make some predictions. They're asking you a residual question. Okay, exponential we did yesterday, and today, power we just did today. Okay, the other, or one of the other, Chapter 3 curve fittings that we're doing is a logarithmic of best fit. Now, what happens here is sometimes it gets confused by some students with logistics. Stat, calc. The one you want for a logarithmic regression of best fit is the ln reg. Okay, your calculator only does logs of best fit base E, or natural log. If you need to convert it into some other log base, then you use the change of base formula or some other skills we talked about in Chapter 3. Okay, the one that you do not want to be using is logistic. Okay, that's the fourth Chapter 4, or it's the fourth Chapter 3 type of curve fitting that we're going to be investigating, and that's the next lesson, which, assuming this isn't on a Friday, will be tomorrow. All right, the last part here. You're given a data set, and what you need to do is decide which of these models is the best. So one of them is just a straight up linear reg, or a line of best fit. Natural log of best fit we just talked about. Exponential power of best fit. So record your A and B values for each one of those models. Make sure your diagnostics are turned on. So you're getting your R and R squared for each one of those. Decide of those four options which one is the best. And you're going to base your answer on R squared. And then once you decide which one's best, then do a couple of predictions. And I think that is enough in terms of what you need to know for tonight's homework, which in turn I believe is enough for this particular video.